In our last video, we looked at the orientation of magnetic fields, moving charges, and forces. Now we're going to look at the amount of magnetic field, force, and charge. So we're going to quantify what we studied in the last section. So in the last section, let's see, we looked at the force on a charged particle moving in a magnetic field. And now we're going to quantify that. So the relationship between the force of the magnetic field and the charge and its velocity are given here. And often you'll see this written as the magnetic force is equal to Q times V times B. In fact, remember that these items these quantities are vectors. Force is a vector. Charge is a scalar. Velocity is a vector, though. And magnetic field is a vector. It has a direction to it. And this is actually a cross product, what's called a cross product in mathematics, which is a fancy way of saying that we're going to take the sine of the angle between the velocity and the magnetic field. So if I go back up to my diagram from up here, if the velocity and the magnetic field are not perfectly perpendicular, then we're only going to take the perpendicular component. We're only going to take the perpendicular component of the velocity to the magnetic field. Let's see. So this force is measured in newtons. And that's the units for that. The charge is measured in coulombs. The velocity is measured in meters per second. And magnetic field is measured in Tesla, named after Nikola Tesla. And once again, I'll just write here that theta is the angle between the velocity and the magnetic field. Okay, we want the perpendicular components. Okay, so what about a wire? Because a wire also carries charges. Those charges are moving at a certain speed. And it turns out that we can basically work out a very, very similar formula, which I have here. The magnetic force equals B times I times L. So I'm going to adjust this a little bit. The magnetic force vector is equal to the current vector. Current has direction, right? Times the length of the wire. And we're going to do, what's called a cross product with the magnetic field, which again means we're going to take the perpendicular component. And pardon me, because back here I should have taken these off. Oops. Once we do a cross product, we don't need to worry about the direction. And we are going to rely on the right-hand rules for direction, much like we rely on force diagrams for direction in other parts of physics. Okay, so the magnetic force is going to equal B I L times the sine of theta, where theta is the angle between I and B. Now look at what happens when we take the units for this. So let me go back up to this handy new formula. Force is measured in newtons. Magnetic field is measured in Tesla. Oops. Current is measured in coulombs per second. And length is measured in meters. And basically, when I go back to my previous formula, look at this. Coulombs times meters divided by seconds times Tesla. Here I've got Tesla times coulombs times meters divided by seconds. It's the same thing in a different order. It's exactly the same thing. Okay, so let's see if we can solve some practice problems here. Practice problem number 1. A thin 1 meter long copper rod has a mass of 50 grams. What is the minimum current needed to cause it to float in a magnetic field of 2 Tesla? Okay, so what I'm going to do is make a sketch. Oops. So there's my segment of wire. I'm just looking at a segment. It's part of a circuit, so there's got to be more to it, but I'm just going to be thinking about this segment right now. Now, the wire is floating due to magnetic force. So there's a magnetic force pushing up on it, and then it's got a gravitational force on it. And in order for it to be floating, those two forces must be equal and opposite. We know that the mass of this thing is 50 grams, which is 0.050 kilograms, which if I multiply that by 9.81 is 0.4905. Oops, I shouldn't say equals. I should say that Fg equals 0.050 times 9.81, which is, here we go, 0.4905 newtons, okay? And that's going to be equal and opposite to both the Fg and the magnetic force are equal and opposite, and I've got the value there. Okay. So what else do I know? I know that the magnetic field is 2 Tesla. I know that the length of the wire is 1 meter. And I'd like to know the current. And it looks like I must assume here that the magnetic field is oriented in the right direction because I don't have any information about angles. So I'm going to go with it, and I'm going to say that F equals BIL. I'm going to assume that everything is perfectly perpendicular. The force that I need is 0.4905. The magnetic field is 2. The current is what I'm looking for, and the length is 1. And when I solve this, I get a current of 0.25 amps. Okay, so mathematically, maybe not too hard, but it's learning all the variables and thinking through the physics of it, the physical setup. Let's try another one. A proton moves eastward in the plane of the Earth's magnetic equator so that the distance from the ground remains constant. What is the speed of the proton if the Earth's magnetic field points north and has a magnitude of 5 times 10 to the negative 5th Tesla? Okay, so just a reminder, let's think about the Earth for a second. So we talked about how the north geographical pole is actually a south magnetic pole, and the south geographical pole is actually a north magnetic pole. And if I were to draw the magnetic field around the Earth, it's three-dimensional. Ooh, and this is something that's shown in that electromagnetism video, also something we can talk about more in class. But the magnetic field would look something like that. And at the equator is right in the middle of the Earth. Ooh, that's not so hot. Okay, so we're at the equator where, if I could zoom in, That magnetic field is basically parallel to the ground. Okay, so I've got this magnetic field, and there's going to be a proton. Proton's moving to the east. We always want to remember our cardinal directions. What do you use to remember your cardinal directions? I grew up near Lake Michigan, so for me, east was where the lake was. That's how I remembered. Think about something in your everyday world that would help you remember north, south, east, and west. Anyway, okay, so we've got that. Let's see. We've got the magnitude of the magnetic field. Magnetic field is 5.0 times 10 to the negative fifth Tesla. And I've got some information that's not listed here. The mass of a proton is 1.67 times 10 to the negative 27th kilograms. That's on the equation sheet. And so what I'm going to assume here is much like this last question. I'm going to assume that the magnetic force equals the gravitational force on the proton, which would be 1.67 times 10 to the negative 27th kilograms times 9.81, which is going to be 1.64 times 10 to the negative 26th newtons. Okay, so I've got magnetic force, I've got magnetic field strength. I also know the charge on a proton, don't I? The charge on a proton is the same as the charge on an electron. It's 1.6 times 10 to the negative 19th coulombs. All right, now we're cooking. Oops. Because now I can use my formula. F equals QVB, and I'm looking for a velocity. So I'm going to plug in my numbers. 1.64 times 10 to the negative 26th equals 1.6 times 10 to the negative 19th times velocity times 5 times 10 to the negative 5th. And when I solve that, I get a velocity, it's rather slow, 0.002 meters per second. It's almost drifting. All right. Okay. One more set of ideas. If you think back to one of the examples that we looked at in the physics aviary, this magnetic field around a wire, we can see that the field strength gets weaker as we get farther from the wire, and there's a formula for that. And it's this. The magnetic field is equal to a constant times the current, divided by 2 pi r. So B is the magnetic field that we're looking for. Mu is permeability of a vacuum. We've used that number before, 4 pi times 10 to the negative 7th. I is the current in the wire, and R is the distance from the wire. So let's do a quick example here. Find the strength of the magnetic field created by a wire carrying 2 amps of current at a distance of 2 centimeters from the wire. So you could use that right-hand rule to determine the orientation of that magnetic field. I'll just sketch it for reminder's sake here. Something like that. And if we wanted to know, let's say this is a distance of 2 centimeters. If we wanted to know the B field at that point, I would plug into the formula. So mu is 4 pi, times 10 to the negative 7th. It's not a coincidence that there's pi here, because this is a circle. The current is 2 amps, and then we've got 2 pi over the radius is going to be that 2 centimeters, which is 0.02. And when we solve that, we would get 2 times 10 to the negative 5th Tesla. And again, magnetic field is measured in Tesla. Okay, another question, last one for today. So note, suppose a second wire of mass 2 grams is placed 2 centimeters above the first. What current is required to make the second wire float above the first? All right. So we've got the magnetic field. Oops. At that point, we just figured it out. The magnetic field at this point is 2 times 10 to the 5th Tesla. 2 times 10 to the negative 5th Tesla, pardon me. So what we're doing now is we're coming in with a second wire. It's going to have a current in, we saw earlier that currents in the same direction attract, so the current must be in the opposite direction. We want to know what that current is. We are going to need a force, a magnetic force that's going to hold up the weight of this wire. So the magnetic force is going to equal the force of gravity on the wire, which is going to be 0.002 times 9.81. And what does that give us? 0.01962 newtons. That's the magnetic force that we need. Current is what we want. And we don't have the length of this wire. So we may have to give our answer in terms of length of the wire. It would be nice if they would have told us the length here. The density of the wire matters. Okay, so we've got F equals BIL, 0.01962 equals 2 times 10 to the negative 5th times I times L. Let's see what we get here. So I get 981 equals IL. Now, if I divide both sides by L, check this out, I get that the current needs to be 981 amps per meter of wire. So I'm going to have to answer it that way. Depending on how long that wire is, I'm going to need 981 amps per 1 meter of wire, or per length of wire. That's quite a bit of current.